So in this section, we're going to be focusing on some techniques for integrating trigonometric functions where maybe antiderivative formulas or a very basic u substitution procedure may fall short of being helpful for us. So to kind of get started, let's revisit an integral that was on the worksheet from last section, integration by parts, cosine cubed x dx. Now there's a number of ways we could handle this, and doing them correctly will lead to equivalent answers. But most of those ways are going to require us to start by breaking up our cosine cubed integrand as cosine squared times cosine. Now, since we've just learned integration by parts, it's our shiny new integration technique, we might be compelled to do an integration by parts, which is definitely one viable way of approaching this problem. So if we had done that, let's see what we'd end up with. So we'd have the integral of, let's see, cosine cubed x dx, and we talked about the idea that we're probably going to need to break this up as cosine squared x times cosine x dx. Especially in the context of integration by parts, we can see that having this product of two functions of x is gonna be helpful. So let's consider how the integration by parts would go down. So we need to think about what we can integrate and what we can differentiate. Integrating cosine squared, while not impossible, would be more difficult than integrating cosine. So for that reason, we would probably go and use cosine dx as our dv and cosine squared as our u. So I'm going to call this is our integration by parts, and we're going to let u equal cosine squared x, and we're going to let dv be just the cosine of x dx. Now, differentiating our u is a chain rule, and by doing the chain rule we're going to end up with negative 2 cosine x sine of x dx. If we do our chain rule and kind of rearrange things to pull our coefficients in the negative out front, and then our v, by integrating cosine, is just going to give us sine of x. Alright, so now we're ready to go ahead and do our integration by parts here. And if we did, we would have u times v, so we'd have sine of x times cosine squared x, so that's our uv, and then minus the integral of v du. And when we bring all of that together, we're going to have negative 2 sine squared, because we've got two sines, and then cosine of x dx. And we could clean this up a little bit. We'd have, I'll just leave this as sine x cosine squared x, and then we pull that negative 2 out to make that plus 2 sine squared x cosine x dx. And now at this point, with this integral, again we have some options here. We could do another integration by parts, but you might remember from some of our examples of the substitution method, this one we could actually handle using substitution. So I'm going to go ahead and I'm going to use substitution for this one. So if we were to do a substitution over here instead of integration by parts, we would choose our u as sine of x, and our du would end up being cosine of x dx. So that integral now becomes the integral of u squared du, which is pretty easy to handle. That's just going to end up giving us what, 1/3 u cubed plus plus c. So we'll take care of that plus c later on. And that would just give us 1/3 sine cubed of x. So if we go back to this problem now, which we're still, remember, we're still working through our initial integration by parts, we'd have sine of x, cosine squared of x, plus 2 times the result of our substitution over here, which was 1/3 sine cubed of x. And then we've got our plus c. So in the end, we could say that our resulting integral gives us sine of x times cosine squared of x plus 2/3 sine cubed x plus c. So not a quick problem. You know, integration by parts can take some time in and of itself, and then throw in an extra substitution to get that done, and that takes some time. So in this section, we're gonna learn techniques that I think are pretty well characterized by an alternative to solving this problem. So let's go back to our cosine cubed equals cosine squared times cosine of x dx. So we've got the integral of cosine cubed x dx. We pull off a cosine from that, one factor of cosine, which leaves us cosine squared times cosine of x dx. And what we're going to do here is we're going to take this cosine squared and we're going to rewrite that using the Pythagorean identity, that sine squared plus cosine squared equals 1. And the motivation for doing that, I think, is going to be clear in just a minute. So if we were to write this as the integral of 1 minus sine squared of x times cosine of x dx. Now if we got parentheses. So if we look at our options here, it may not be immediately obvious, but we are going to be able to get out of this by just doing one u substitution. If we were to let, in this case, u equal sine of x, that would mean that our du is cosine of x dx. Well, here's our u, here's our du right there, so this integral becomes the integral of 1 minus u squared du. And we can do term by term integration on this, and we'd get u minus, so u minus 1/3 u cubed plus c, which would give us sine of x minus 1/3 sine cubed of x plus c. Now you may be looking at these two answers and saying, well, they're not the same. They are equivalent. This would be a great exercise for you to try on your own, but if you had gone up to this first example and in place of that cosine squared put 1 minus sine squared x and then distributed everything, you would get back to this solution. So two different ways, they yield two equivalent answers, but I feel the second one is much easier. And this, as I'd mentioned, this characterizes the basic technique we'll be using in this section. And it's good to keep in mind, you know, when we see these products of powers of sines and cosines and other trig functions, oftentimes what we're going to be needing to do is find a way to break up the integrand, and then we'll use various trig identities, often in concert with the substitution method, to work this through. So the good news is really most of these problems will boil down just to substitution. Now, with that in mind, it's good to review a few trig identities that we'll be using quite a bit. The Pythagorean identities, we should be comfortable using all of these. By the way, this is really the only one you'd have to have memorized, because you could generate these other two. by taking this first one, sine squared plus cosine squared equals 1. If you divide everything in that first equation by sine squared, you would get this one. And if you divided everything by cosine squared, you would get this one. So you can generate those relatively simply. The double angle identities, sometimes the cosine double angle identity pops up, but the sine will come up quite a bit. So that's a good one to know. And then these power reducing identities are also going to be very helpful for us. By the way, just to show you, this is also kind of connected with, if you remember from trig, the half angle identities. There's another way that we could express this. Like, maybe it wasn't just cosine squared of x. Maybe we had cosine squared of, say, 5x. That just means that the angle inside that cosine is 5x. The identity would then tell us it's going to be 1 plus the cosine of twice 2 times whatever that angle is. In that case, this would be 10x all over 2. All right, so some trig identities to review. And then lastly, if you haven't already, you're probably going to want to keep these in the front of your mind as you go through problems that involve trig functions. In particular, it's good to recognize what you can differentiate. So we might look at these and remember, hey, I know how to take the derivative of these. So all of these you can differentiate, and these are trig functions that you know how to integrate. This often proves helpful, when we're trying to do things like pick our u's or our u's and dv's, thinking, all right, what am I going to be able to differentiate? Those are going to make good u's. What can I actually integrate? So something worth keeping in mind as we go through this section.